Precipitation regimes identification is an age-old problem, but it's also very important, especially for prediction, agricultural planning, and regional extreme analysis. So on the plot, there are multiple points. Each point stands for a major weather station in China. We have more than 16 years recording of precipitation data in each station. We want to use this data to identify the precipitation regimes in China. The first method that we use is the famous empirical orthogonal function analysis. It's the standard and the classic method in meteorology. It's equivalent to principal component analysis in statistics. But however, the result from EOF was not as good as we expected. So, as we know, that for precipitation data has some special characteristics. Precipitation data are usually spatially and temporally dependent. They are multi-scale, unevenly distributed, and they are heavily related with the local geography. So we decided to develop a model-based clustering of spatial functional data as an alternative to EOF. Here is the model structure. We have observed variable, precipitation data. We also have latent variable, cluster membership. We have covariate geographic data. We assume a functional linear model for observed variable, conditional on latent variable. We assume Markov random field model for latent variable, conditional on covariate. The target of our method is to compute the empirical distribution of latent variable, conditional on observed variable, and covariate. For the functional linear model, the precipitation data can be decomposed into three parts: mean function, time random effect, measurement error. For the mean function can be written as the linear combination of the basis functions. And we assume mean function is the same within a cluster. Here, in equation 1, you can see we have a capital S. Capital S is a basis matrix generated by the B-spline basis function. And actually, capital S can be different for different stations to allow for the missing data in the observation of the precipitation. For the Markov random field model, we should first assume a neighborhood. Given a cluster member of a neighborhood, we can assume the cluster membership for that station follows a Gibbs distribution. Gibbs distribution originally comes from the statistical physics. There's an interaction parameter, theta. So theta measures the interaction degree of the spatial dependence. Actually, here in this model, we can incorporate geographic covariates by modifying UIK, this function. So, using EM algorithm, we can estimate all the parameters in this model. After parameter estimation, we can get the cluster results. This is the old version of the slides. Yeah, okay. Yeah. So there's some difficulties in the computation. For example, we need to incorporate the multi-resolution of the precipitation data, and there's also no analytic form of the joint likelihood because of Markov random field model. So we use weighted likelihood and we assign weights to each curve, and we also use pseudo likelihood. Here is our final results of the precipitation regimes identification in China. There's 14 clusters in total. That's an interesting phenomenon in East Asian. It's called East Asian rainy season. So from the late spring to early summer every year, the wind from the Pacific will bring the warm and humidity to China, Korea, and Japan. And the warm wind will fight with the cold wind from north. So this phenomenon will cause persistent precipitation. So if you check our cluster results, if we pay attention to the 4 clusters on the east of China, we estimate the parameters, so we can get the estimated mean function for each clusters. If we check the peak value of these clusters, their appearing time is consistent with the Eastern Asian rainy seasons. Thank you. Any questions?